The intention of this lab was to measure data collected from an observation of an object in free fall that was experiencing drag force, in other words, falls slower than a rock might. The information from this observation, including time interval of motion, initial velocity, and a calculation of terminal velocity to find drag force, was used when creating a computer simulation of the moving object, given that it was under the force of solely gravity, and another given that it was under the force of both gravity and drag force. These computer simulations allowed for the prediction of motion and change in position of a falling Caulfield filter by using physics concepts like Newton's second law, kinematics formulas for objects in free fall, and the equation for drag force where force is proportional to v squared. The observed motion was recorded using an iPhone and analyzed using the tracker application. Measures were taken to eliminate possible error, including assurance of proper lighting, limiting of the motion of filter that may be perpendicular to the line of recording, and maintenance of an axis throughout by working to remove camera shake. After recording and uploading the video of a falling Caulfield filter, the video was uploaded into Tracker where the axis was set in alignment with the motion of the filter. The frames per second were set to those of an iPhone camera, which were found to be 30 frames per second. The distance was calibrated using a calibration stick. The calibration stick was used to measure the diameter of the Caulfield filter, which was known to be a measurement of 8 centimeters. An additional calibration stick was used to measure the drop height, which was known to be 1 meter. The motion of the filter was recorded at every video frame through the placement of markers on the center of mass of the Caulfield filter. This allowed for the production of a displacement versus time graph through Tracker. To creating a displacement versus time graph using the observed motion, I used GlowScript to simulate the motion of the Caulfield filter, given that the only force acting on it was gravity and that it began with a zero velocity. In the code, I changed the mass of the object to be 0.01353 kilograms, which is the mass of the Caulfield filter. Additionally, the parameter of the time step was set to be 0.033 seconds. Fnet was set to be the vector 0, negative 9.8 times the mass of the filter, 0 newtons. This program utilizes a while loop which iterates through the time by this time step, which is the amount of time between frames in the Tracker program. Each time it iterates through this while loop until reaching 1.4 seconds, which is when the clip ends. The velocity of the ball is updated using the formula B equals V initial plus Fnet divided by mass times delta T, and the position was updated using the formula R equals R initial plus velocity times delta T, where the values R and V are updated during every iteration. This code resulted in the data here. Another GlowScript program was created to simulate the motion of a Caulfield filter, given that it was being acted upon by both gravity and drag force. To do this, the formula F drag equals negative b times v squared times the unit vector of velocity needed to be used, where v would be updated in every iteration of the program. To find the value of b, I used the concept that the force of gravity would be equal to drag force at terminal velocity. So using an area of the observed data where the velocity was constant, I used these values to compute b using the formula mg equals bv, where v is terminal. I used the same program as the one simulating motion with just gravitational force, but updated Fnet to be equal to F gravity plus F drag. This resulted in the data here. All three data sets from the observed and calculated values of the displacement of the filter over time are plotted in this Google Doc. In the graph comparison of the three models, there are distinct differences between the computational model that only includes force of gravity and the observed motion. The object and computational model travel significantly further in this time than either the objects in the other two models. This is because there is no upwards drag force acting on the object in this model to hinder its motion. This motion is of an object that is experiencing no upwards drag force. Another difference in the graphs is that we see that the simulated version of the Caulfield filter that includes both drag and gravitational force travels a bit further than the actual observed filter. This could be attributed to an error in the calibration stick in the Tracker app, not configuring the video to the correct measurements. Additionally, error in the markings of the location of the center of mass of the filter could change the calculated measurement of B, since the observed locations were used to calculate this value, which would also contribute to the distance traveled by the filter being slightly off. Both the observed model and the computational model, which includes the gravitational and drag force, show a period of time in which the filter is at terminal velocity. This can be seen in the graphs where velocity is constant, which is where the slope is constant in the position versus time graphs. This period of time is where the drag and gravitational force are equal and opposite. This is because there is constant velocity and no acceleration, which only occurs when net force is zero. The computational model showing a situation in which only gravitational force is acting upon the object would not have a period of terminal velocity, since there is no opposing force to that of gravity. In the computational model, the terminal velocity can be determined to be negative 0.9249 meters per second. Change the initial velocity in this program to be 5 meters per second in the downward direction, and the final terminal velocity was still negative 0.9249 meters per second. The velocity versus time graphs of these models can be seen here.